17 1.11 Sequence and series, progression, 1 sequence is a sequence is a function, whose domain is the set n of natural numbers or rule set of n. We may also define a sequence as an arrangement of numbers according to a certain fixed rule. The different numbers in sequences are called its terms and are generally denoted by a 1, a 2, a 3, or t1, t2, t3, etc. Some examples of sequences are 1, 3, 5, 7, 9, I, 1, 3, 9, 27, 2, in, I. The terms are arranged such that the difference between two consecutive terms is the same, i.e., 2, in, 2. The terms are arranged in such a way that the ratio of two consecutive terms is the same, i.e., 3. Note: it is obvious that if the rule, which the terms of a sequence obey, is known, then all or any term can be found. General term: the nth term of a sequence is called the general term and is denoted by an or tn. Finite and infinite sequences. Finite sequence: a sequence containing finite number of terms is called a finite sequence. For example, 2, 4, 6, 8, 41, 3, 9, 243, 24, 21, 18, up to 6 terms. Infinite sequence: a sequence is called infinite if it is not a finite sequence, or in other words, a sequence having infinite terms is called an infinite sequence. For example, 1, 3, 5, 7, to infinity 3, 33,333. Note: if the general term equals tn of a sequence is given, we can find t1, t2, t3 by putting n equals 1, 2, 3 in tn 1, 1, 1, 2 series, the terms of a sequence connected by plus v or v sign from a series. For example, 1 plus 3 plus 5 plus 7 plus. The different terms of the series are denoted by or t1, t2, t3. Solved examples. Example 1. Write the first 3 terms of the sequences whose nth terms are I, 3 and 5, 2, 2n, 3, n2. Solution: I. Here tn equals 3 and 5. Putting n equals 1, 2, 3 in tn, we get t1 equals 3.1 to 5 equals 2, t2 equals 3.2 to 5 equals 1, t3 equals 3.3 to 5 equals 4, 2. Here tn equals 2n. Putting n equals 1, 2, 3 in tn, we get t3 equals 23 equals 8, t1 equals 21 equals 2, t2 equals 22 equals 4, 3. Here tn equals n2. Putting n equals 1, 2, 3 in tn, we get t1 equals 12 equals 1, t2 equals 22 equals 4, t3 equals 32 equals 9. Example 2. If tn equals n2, when n is odd, and tn equals 2n, when n is even, then write down the first 3 terms. Solution: here tn equals n2, when n is odd. Putting n equals 1, 3, 5, we get t1 equals 12 equals 1, t3 equals 32 equals 9, t5 equals 52 equals 25. Also, tn equals 2n, when n is even. Putting n equals 2, 4, 6, we get t2 equals 2.2 equals 4, t4 equals 2.4 equals 8, t6 equals 2.6 equals 12. Hence, the first 6 terms of the sequence are 1, 4, 9, 8, 25, 12. Example 3. If tn equals n1, n2, n3, show that the first 3 terms of the sequence are 0, but the rest of the terms are positive. Solution: here tn equals n1, n2, n3. Putting n equals 1, 2, 3 in tn successively, we get t1 equals 1, 1, 1, 2, 1, 3 equals 0, t2 equals 2, 1, 2, 2, 2, 3 equals 0, t3 equals 3, 1, 3, 2, 3, 3 equals 0. For n, 3, each of the terms, n1, n2, and n3, is positive, and hence their product, n1, n2, n3, is also positive. Hence, the first 3 terms are 0, but the rest of the terms are positive. 1.12 Arithmetic progression. An arithmetic progression is a sequence whose terms increase or decrease by a constant number called the common difference. A series in arithmetic progression thus becomes an additive series in which the common difference can be found by subtracting each term from its preceding one. Thus, the sequence 1, 5, 9, 13, 17, 21, 25, is an infinite arithmetic progression of 7 terms. The first term is 1 and the common difference is 4. Similarly, 2, the sequence 12, 5, 2, 9, is an infinite arithmetic progression of 4 terms. The first term is 12 and the common difference is 7. The corresponding arithmetic series are 1 plus 5 plus 9 plus 13 plus 17 plus 21 plus 25 plus 2, 11 plus 17 plus 23 plus 29 plus. Thus if the first term and common difference are known, the AP is completely known. the arithmetic progression a plus d, a plus 2d, a plus 3d, whose first term is a and the common difference is d, is designated as the standard form of the arithmetic progression. 19. The corresponding arithmetic series a plus d, plus, a plus 2d, plus, a plus 3d, plus, is designated as the standard form of an arithmetic series. The abbreviation AP, for arithmetic progression is commonly used. In other words, a sequence in which Tn1 equals constant difference, say d, is called an AP. This difference is called the common difference and is denoted by d. Note 1. In general, a plus d, a plus 2d, represents an AP whose first term is t1 and common difference is d2. Nth term t1 of an AP is called its general term. Nth term of an AP, let the AP be an a plus d, a plus 2d, a plus 3d, whose first term equals a and common difference equals d. Then t1 equals a plus 1 d equals a plus 0 d, t2 equals a plus d equals a plus 2 d, t3 equals a plus 2 d equals a plus 3 d equals, and so on. So, nth term of an AP is Tn equals a plus n1 d. Properties of an AP: if each of the term of an AP is I increased by 2, decreased by 3, multiplied by 4, divided by a constant quantity, then the resulting sequence is still an AP. Let the AP be a plus d, a plus 2d, and k is a constant quantity. Then, if we add, subtract, multiply or divide the series by k, then it will still remain an AP. Example 1. Find the 12th term of the AP 3, 7, 44, 15. Solution. Here it equals 3, d equals 7, 3 equals 4, so Tn equals a plus n1, dt 12 equals 3 plus 12, 1, 4 equals 3 plus 44 equals 47. Example 2. Which term of series 12 plus 9 plus 6 plus is equal to I, 30, to 100? Solution. I, the series in an AP with first term 12 and common difference minus 3. Tn equals a plus n1, d equals 12 plus n1, 3, equals 15, 3, and suppose the nth term is 30, then 15, 3, n equals 30, n equals 15, so 30 is the 15th term. 2. Now suppose that Tn equals 100, 15, 3, n equals 100, which is impossible, because n must be a whole number. Hence there exists no term in the series which is equal to 100, n equals 115, 3. 20. Sum of the first n terms of the general AP. The sum of a series in AP is an important quantity which yields many other related results. We denote the sum of n terms by Sn and the first and last terms of the sequence by a and l respectively. Let Sn denote the sum of n terms, then note, generally, formula, I, is used when the last term is given and, 2, is used when common difference is given. Example 1. 20. Sum of the first n terms of the general AP. The sum of a series in AP is an important quantity which yields many other related results. We denote the sum of n terms by Sn and the first and last terms of the sequence by a and l respectively. Let Sn denote the sum of n terms, then note, generally, formula, I. 20. Sum of the first n terms. 20. Sum of the first n terms of the general AP. The sum of a series in AP is an important quantity which yields many other related results. We denote the sum of n terms by Sn and the first and last terms of the sequence by a and l respectively. Let Sn denote the sum of n terms, then note, generally, formula, I, is used when the last term is given and, 2, is used when common difference is given. Example 1. Find the sum of the series 72 plus 70 plus 68 plus 40. Example 3. Find the sum of 20. Sum of the first n terms of the general AP. The sum of a series in AP is an important quantity which yields many other related results. We denote the sum of n terms by Sn and the first and last terms of the sequence by a and l respectively. Let Sn denote the sum of n terms, then note, generally, formula, I, is used when the last term is given and, 2, is used when common difference is given. Example 1. Find the sum of the series 72 plus 70 plus 68 plus 40. Example 3. Find the sum of all numbers between 100 and 1000, which are divisible by 11. Solution. Numbers between 100 and 1000 divisible by 11 are 110, 121, 132, 990, which clearly form an AP, where first term, a equals 110, the common difference d equals 11, and the nth term Tn equals 990. Then, we have Tn equals a plus, n1, d 990 equals 110, n1, 11, i, n equals 81. So the sum of these numbers is given by Sn equals n, a plus L, 2 Sn equals 81, 110 plus 990, equals 44,552 Sn equals a plus D, plus, a plus 2D, plus L2D, plus L, D, plus L, 1. Writing the above series in reverse order, we have Sn equals L plus L, D, plus L2D, plus a plus 2D, plus a plus D, plus a 2 adding 1 and 2, we get to Sn equals a plus L, plus a plus L, plus a plus L, plus up to n terms equals n, a plus L, 2, 1, a n Sn but L equals a plus n1, D2, 1, dn of n Sn solution. The given series is an AP with a equals 72 and D equals minus 2. Let n be the number of terms. Then Tn equals 40, a plus, n1, D equals 40 72 plus, n1, minus 2, equals 40, i.e., 2n equals 34 or n equals 17. Now 2, 1, a n Sn example 2. The first and the last term of an AP are respectively 4 and 146, and the sum of the AP equals 7,171. Find the number of terms of the AP and also its common difference. Solution. We have A equals 4 and L equals 146 and Sn equals 7,171. Let n be the number of terms of the AP 7,171 2, 146, 4, 7,171, 2, 1, NSN or NSNN equals 101, also 146 equals 4, plus 101 1, D 100 D equals 146 plus 4 equals 150 D equals 1.5. Hence n equals 101 and D equals 1.5. 21 Arithmetic mean, AM if A, B are an AP, then A is the AM, between A and B, i.e., if three quantities are an AP, then the middle one is defined as AM, between the other two. Arithmetic mean between A and B, let A be the AM, between A and B, so, A, B are an AP to insert n AMs between two quantities and B, let A1, A2, A3, and be the n AMs between A and B, so, A1, A2, A3, and B are an AP. Example 4. Find the series whose sum to n terms is 5n2 plus 3n. Solution. Given that Sn equals 5n2 plus 3n, pitting n equals 1, and 2, we get S1 equals 5, 1, 2 plus 3, 1, equals 8 and S2 equals 5, 2, 2 plus 3, 2, equals 26. Now first term, A equals S1 equals 8, second term S2, S1 equals 26, 8 equals 18. Then the common difference, D equals second term, first term equals 18, 8 equals 10. Hence, the required AP is 8, 18, 28, 38, C, 13 plus 23 plus 33 plus n3 equals n plus 1, 2, 2, 1 plus 2 plus 3 plus n equals n plus 1, 2, B, 12 plus 22 plus 32 plus n2 equals n plus 1, 2n plus 1. To some important formulae thus, A equals B, i.e., 2A equals A plus B. Similarly, A equals A plus B2 in this AP, the first term is A, the last term is B and the number of terms is n plus 2, i.e., B is the n plus 2, term equals A plus, n plus 2 1, D equals A plus, n plus 1, D, which are the required arithmetic means between A and B. D equals B, a n plus 1 A1 equals A plus D equals A plus B, a n plus 1 A2 equals A plus 2 D equals A plus 2B. A n plus 1, an equals A plus n D equals A plus nb, n plus 1. 22 Example 1. The first and the 8 terms of an AP series are 2 and 23 respectively. Find the 10th term of the series. Solution. Let common difference equals DT8 equals 2 plus 8, 1, D23 equals 2 plus 7 D equals 3, 10th term TT10 equals 2 plus 10, 1, 3 equals 29 Example 2. The PTH, QTH, and RTH terms of an AP series are A, B, and C respectively. Prove that QR, A plus, R, P, B plus, P, Q, C equals 0. Solution. Let the first term equals A, and the common